Hello students, welcome to this lecture on Causal IIR Wiener filter. Let us recall the output x hat n of a non-causal IIR filter is given by this equation. We discussed non-causal IIR filter in the last class and the filter output is given by this equation. The filter coefficients Hs are obtained by minimizing the mean square error. Mean square error is given by this expression E of x n minus summation h I into y n minus I going from minus infinity to infinity whole square. So, we have to minimize this expression with respect to Hj. Now, after applying the orthogonality principle, we got the WH equation, that is Wiener-Hopf equations, which are given by this relationship summation h I into r y j minus I going from minus infinity to infinity is equal to r x y j for j going from minus infinity to infinity. So, this is an infinite set of equations and these equations can be solved in the transform domain. By applying the Z transform, we get this relationship Hz is equal to Sxyz divided by Syz, that is the cross power spectral density divided by power spectral density of the observed data. So, this is the Wiener filter relationship in the case of non-causal IIR Wiener filter, and this is quite simple. The problem with non-causal IIR Wiener filter is that it is not realizable in real time. We cannot implement it in real time. This lecture will explore the causal IIR Wiener filter which is realizable in real time. Let us consider this filtering problem. Consider the IIR filter to estimate signal x n as shown in figure below. This is the figure. Here x n plus v n, that is our observed signal y n, and we apply the IIR Wiener filter with filter coefficient h n to get the estimated signal x hat n. So, this is the IIR Wiener filter structure. There are infinite number of coefficients from h0 to h infinity. The estimator x hat n is given by x hat n is equal to summation h I y of n minus I going from 0 to infinity, because h i's are non-zero for I greater than equal to 0. The mean square error of estimation is given by this expression E of E square n, that is equal to E of x n minus x hat n whole square, and if we substitute x hat n equals this, then we get E of E square n equal to E of x n minus summation h I y n minus I going from 0 to infinity whole square. So, this mean square error we have to minimize with respect to each hj. There are infinite number of hj's are there. With respect to each hj, we have to minimize this expression to get the optimal estimator. Now, we can apply the orthogonality principle and get the Wiener-Hopf equations. So, applying the orthogonality principle, we will get, that is, this part is error is orthogonal to each data point. So, that way E of x n minus summation h I y n minus I going from 0 to infinity into y n minus j must be equal to 0 for j is equal to 0 to infinity. So, this is the orthogonality relationship which we have studied earlier. Now, since we are considering WSS process, so y n minus j into y n minus I, that will be r y of j minus I. Similarly, x n into y n minus j, if we take the expectation, we will get r x y j. Therefore, we will get the Wiener-Hopf equation, that is given by summation hi ry into j minus I going from 0 to infinity, that is equal to rxyj for j equal to 0 to infinity. So, we have got the Wiener-Hopf equations corresponding to causal IIR Wiener filter. Now, we have to solve this infinite set of equations to find out hi for I is equal to 0 to infinity. Now, what are the difficulties in solving the Wiener-Hopf equations for causal IIR Wiener filters? As the number of equations are infinite, they are better solved in the Z transform domain. We cannot directly apply the convolution theorem of Z transform, because hi sequence, that filter coefficient sequence, is a one-sided sequence, while that autocorrelation sequence is a two-sided sequence. Thus, we have hi non-zero for I is equal to 0 to infinity, but ry non-zero for I is equal to minus infinity to infinity. So, because of this, we cannot apply the convolution theorem of Z transform on the Wiener-Hopf equations. Here comes Wiener's contribution. The analysis is based on the spectral factorization theorem for a regular random process, that is Syz is product of 3 factors sigma v square into Hcz into Hcz inverse, and Hcz is a causal minimum phase transfer function, and sigma v square is the variance of the innovation process. So, by applying spectral factorization, we have Syz is equal to sigma v square into Hcz into Hcz inverse. Now, we can apply the whitening filter, because Hcz is a causal minimum phase filter, therefore, we can invert it. So, we can apply the whitening filter H1z is equal to 1 by Hcz to generate the innovation process Vn. This Vn is the innovation process. So, this is the filtering action. We pass Yn through H1z is equal to 1 by Hcz, we will get Vn. Now, Vn is an uncorrelated sequence. It is easy to estimate action from this Vn sequence. So, we will estimate action from Vn by using the causal IIR Wiener filter principle. So, Vn you pass it through S to Z, we will get x at n. The filter S to Z is now used to estimate action from Vn using the linear minimum mean square error criterion. Then the causal Wiener filter will be Hz is equal to H1z into H2z, where H1z is equal to 1 by Hcz as we have shown earlier. This is the H1z. So, we pass Yn through H1z, we get Vn, and then using H2z we get x at n. Therefore, our Wiener filter will be the cascaded filters H1z and H2z, or in other words our Hz will be H1z into H2z. Let H2n be the Wiener filter coefficients to estimate action from the innovation process Vn. So, here corresponding time interval parameters are H2n. The estimator x at n is now given by x at n is equal to summation H2i v of n minus I going from 0 to infinity, and the corresponding minimization problem is minimize E of xn minus summation H2i into v of n minus I going from 0 to infinity whole square with respect to H2j, j going from 0 to infinity. Now we will get the Wiener filter for the innovation process. Applying the orthogonality principle results in the Wiener-Hoff equations like this: E of xn minus summation h2i into v of n minus I going from 0 to infinity. This is the error, and it is orthogonal to v of n minus j going from 0 to infinity. Therefore, E of xn minus summation h2i into v of n minus I going from 0 to infinity into v of n minus j must be equal to 0 for j is equal to 0 to infinity. Now, taking the expectation operation, we will get that summation h2i into rv j minus I going from 0 to infinity, that must be equal to rxv j going from 0 to infinity. So, this set of equations are the Wiener-Hoff equations for the innovation process. Note that RVM is equal to sigma v square into delta m. Because innovation sequence is a white noise sequence, therefore, its autocorrelation function is sigma v square into delta m. It is sigma v square for m is equal to 0 and 0 otherwise. Therefore, we will write this expression here. Therefore, we will get summation h2i sigma v square delta j minus I going from 0 to infinity, that must be equal to rxv of j for j equal to 0 to infinity. Now, this expression using the property of delta function, we get h2j into sigma v square, that must be equal to rxv of j for j is equal to 0 to infinity, which gives h2 of j is equal to rxv of j divided by sigma v square, and this is for j is equal to 0 to infinity. So, we are able to find h2j since our input process is a white noise process, and taking the z transform of h2j, we will get h2z is equal to z transform of this divided by sigma v square. So, z transform of h2j must be equal to z transform of rxv of j divided by sigma v square. But here j is defined for 0 to infinity. Therefore, we have to consider only the positive part of the z transform, that is h2 of z is equal to positive part of sxv z divided by sigma v square, where sxv z plus is the positive part, that is the part containing the non-positive powers of z, that is z to the power 0, z to the power minus 1, z to the power minus 2, etc. in the power series expansion of sxv z. Therefore, h2z will be given by the positive part of sxv z divided by sigma v square. So, how to determine h2z? We know that Vn is equal to summation I is equal to 0 to infinity h1 I into y n minus I. So, this is from the innovation representation of yn. So, we get this relationship, and taking the autocorrelation function, we will get rxv of j is equal to E of xn into Vn minus j. So, therefore, the rxv of j will be equal to summation h1 I into E of xn into y n minus j minus I going from 0 to infinity. That will be equal to summation h1 I into rxy j plus I, because E of xn into y n minus j minus I will give me rxy of j plus I. And now, if we take the z transform, sxv z will be equal to h1 z inverse into sxy z. Here j plus I, because of that this is h1 of z inverse into Sxy of z. And I know H1 of z inverse is equal to 1 by Hc z inverse. Therefore, Sxv of z will be 1 by Hc z inverse into Sxy z. So, we have H2 of z is equal to Sxv of z plus divided by sigma v square. Therefore, we will substitute this expression. So, we will get H2 z is equal to 1 by sigma v square into Sxy of z divided by Hc of z inverse plus means the positive part. Therefore, the causal IIR Wiener filter is given by Hz, which is equal to H1z into H2z, and H1z is given by 1 by Hcz and H2z is given by this. Therefore, the combined expression will be 1 by sigma v square into Hcz into positive part of Sxyz divided by Hc z inverse. So, this is the causal IIR Wiener filter expression. Let us see the computing steps. We have to find the power spectral density Syz using the available model or estimate it from the data. We have to find the cross power spectrum Sxyz using the available model or estimate it from the data. Then we have to factorize Syz using the spectral factorization theorem. Syz is equal to sigma v square into Hcz into Hcz inverse. If these things are available, then the transfer function of the IIR Wiener filter is given by Hz, that is equal to 1 by sigma v square into Hcz into the positive part of Sxyz divided by Hcz inverse. So, Hcz inverse we get here, Hcz also we get here, sigma v square also we will get here, and Sxyz we estimate or find from the model here. We can represent the procedure in a block diagram. Yn is passed through this filter of transfer function 1 by Hcz to get the innovation process Vn, which is now passed through this filter 1 by sigma v square into the positive part of Sxyz divided by Hcz inverse, and we will get the estimator x at n. This is the principle of causal IIR Wiener filter. We have to find the mean square estimation error for the causal IIR Wiener filter, and it is given by E of E square n, which can be written as E of E n into x n minus summation h I into y n minus I going from 0 to infinity. And using the orthogonality principle, we will get this expression is equal to E of E n into x n. Again we are expanding E n. So, we will get E of x n minus summation h I into y n minus I going from 0 to infinity into x n. And after taking the expectation operation, we will get E of x n into x n, that is R x of 0. Similarly, this part will be summation h I into R x y I going from 0 to infinity. So, this is the mean square error of estimation. And in terms of the transfer function, we can get it in the frequency domain. R x of 0 is equal to 1 by 2 pi integration of S x omega d omega from minus pi to pi minus 1 by 2 pi integration from minus pi to pi of h omega into S x y star omega d omega. So, this is the expression for the mean square estimation error, which we get by applying the inverse DTFT. Now, this same integral we can get in the Z transform domain also, where we have to perform the contour integral over a contour that include the unit circle. So, we will consider one contour suppose in the Z plane, This is the z plane, and this is the contour C, which include the unit circle. Maybe somewhere unit circle is here. This is unit circle. So if we perform this integral over this unit circle, that is contour integral of Sxz minus Hz into Sxyz inverse into Z inverse dz, we will get the mean square error. So this way we can find out the mean square estimation error. Let us consider one example. Consider the signal Yn is equal to Xn plus Vn with Vn as a Gaussian white noise of variance 1 and Xn given by this model, Xn equal to 0.8 Xn minus 1 plus Wn, where Wn is a white noise with variance 0.68. This signal Xn and the noise Vn are uncorrelated. Find the optimal causal Wiener filter to estimate Xn. So first we will see what is the power spectral density of Xn. So that way this model, this is AR1 model, you are passing Wn, that is the white noise, through the filter 1 by 1 minus 0.8 Z inverse, and we will get Xn, that is the WSS output. So we can find out the power spectral density of Xn, that is given by Sxz, which is equal to 0.68, that is the variance of Wn, divided by 1 minus 0.8 Z inverse, that is Hz, into 1 minus 0.8 Z, which is Hz inverse. So that way we can find out the power spectral density of Xn. Sxz is given by this. And since Vn is a white noise of variance 1, its power spectral density is equal to 1. So we have to find out the power spectral density of Yn. So this is my Yn, and I know that autocorrelation function of Yn is equal to autocorrelation function of Xn plus autocorrelation function of Vn, that we have analyzed earlier. Therefore, we will get Syz, that is power spectral density of Y, is equal to Sxz plus Svz, and this can be written like this: 0.68 divided by 1 minus 0.8 Z inverse into 1 minus 0.8 Z plus 1. So this is the power spectral density for Yn. Simplifying and factorizing, we will get this Syz can be written as this expression: 2 into 1 minus 0.4 Z inverse into 1 minus 0.4 Z divided by 1 minus 0.8 Z inverse into 1 minus 0.8 Z. So from this we will get sigma v square is equal to 2, and causal part is 1 minus 0.4 Z inverse divided by 1 minus 0.8 Z inverse. This is the causal transfer function. Therefore, Hcz will be equal to 1 minus 0.4 Z inverse divided by 1 minus 0.8 Z inverse. Also, because it is signal and noise are uncorrelated, therefore we will get from the same model Sxyz is equal to simply Sxz, and which is given by 0.68 divided by 1 minus 0.8 Z inverse into 1 minus 0.8 Z. So we have found out Sxyz, we have found out Hcz, and we have the Hcz inverse also. This part is the Hcz inverse. Now Hz is equal to 1 by sigma v square into Hcz into positive part of Sxyz divided by Hcz inverse. So we will substitute each term: sigma v square is equal to 2, Hcz is equal to this part, and this part also Sxyz is equal to this part, and similarly Hcz inverse is this part. So, ultimately we will get an expression like this. We have to consider the positive part of this, and we can get the positive part of this expression, this Z transform, by partial expansion of this quantity 0.68 divided by 1 minus 0.8 Z inverse into 1 minus 0.4 Z. So, if we have the partial expansion and take the part containing 1 minus 0.8 Z inverse as the denominator, that part will be the positive part of the Z transform, because that part only will contain the non-positive powers of Z. So, therefore, we will take that part and then simplify with this, and ultimately we will get Hz equal to 0.944 divided by 1 minus 0.4 Z inverse. So, this is the transfer function of the IIR Causal Wiener filter, and correspondingly Hn also we can find out by taking the inverse transform. Hn will be 0.944 into 0.4 to the power n for n greater than equal to 0. This will be defined for n equal to 0 to infinity. So, that way we can find out the causal IIR Wiener filter. Let us summarize the lecture. The estimator x hat n using the causal IIR Wiener filter is given by this relationship. X hat n is equal to summation h I into y n minus I going from 0 to infinity. The mean square error E of E square n, that is equal to E of x n minus x hat n whole square, is minimized with respect to each h j to get the optimal estimator, and the optimal estimator is given by the Wiener-Hopf equations, summation h I into r y j minus I going from 0 to infinity is equal to r x y of j for j is equal to 0 to infinity. And this set of Wiener-Hopf equations cannot be solved directly in the transform domain. Therefore, we applied the spectral factorization theorem. Syz is equal to sigma v square into Hcz into Hc z inverse. Then we applied the whitening filter H1z is equal to 1 by Hcz to generate the innovation process Vn. Xn now can be estimated from Vn using the causal IIR Wiener filter, which was derived as H2z equal to 1 by sigma v square into positive part of S xyz divided by Hc z inverse. Finally, the causal IIR Wiener filter is given by Hz, that is equal to 1 by sigma v square into Hcz into the positive part of Sxyz divided by Hc z inverse. So, we have to find Sxy of z, Hc z inverse, Hc z and sigma v square. Then we can find out Hz. Please try to answer the following questions. Why the convolution theorem of Z transform cannot be applied on the Wiener-Hopf equations of causal IIR Wiener filter? So, we noted that we cannot apply the convolution theorem of Z transform directly on the Wiener-Hopf equations of causal IIR Wiener filter. Why? How do you overcome the above problem? Through the innovation representation of the signal Yn. So, these two questions you would try to answer. Thank you.